I'm going to talk through a couple of simple examples for dealing with electromagnetism and special relativity. The first one is going to be very, very simple. It's just a point charge, and we're going to consider it at first in a reference frame S, where the charge is at rest. We assume that it's at rest at the origin, so we know that we can write the scalar potential, or the electric potential, phi, or V if you prefer, is Q over 4 pi epsilon naught R, and the vector potential A is equal to 0. And in this case we can, of course, write the potential for vector as 0, 0, 0, phi over C, which is going to be 0, 0, 0, Q over 4 pi epsilon naught R C. We could write the fields as well, just equally well, but at the moment I think it's slightly easier to use the potentials. Transforming this now to a frame S prime, which has a velocity V is equal to V 0, 0 relative to S. Then we find, let me just put a little bit of a space in there, we find that phi primed over C, because remember we have a 1 over C there, is equal to gamma phi over C, so there's no factor of A in there to change anything, and AX primed is equal to minus gamma V over C, phi over C. And if we just rewrite those, we find that phi primed, let me just change that actually, so phi primed itself, not phi primed over C, is now gamma Q over 4 pi epsilon naught R, and AX primed is minus gamma, then we're going to have a QV, and then there's a mu naught. The mu naught comes from this pair of C's, which gives us a C squared, and then a 1 over epsilon naught. So 1 over C squared is epsilon naught mu naught, and epsilon naught mu naught over epsilon naught is just mu naught. And then that's, that's then divided by 4 pi R. Notice that in both cases we will need to transform the coordinate R, and in the bottom case with A we're going to have to transform R and V. So what does this tell us? This tells us that if we start with what seems to be a very simple electrostatic problem, if we transform to a reference frame moving with respect to that electrostatic problem, we suddenly introduce a magnetic field, because the A will give us a magnetic field. We could, of course, written this in terms of the fields themselves and use the field transforms. And if you're interested, you can use this as a way of calculating the electric and magnetic field for a moving charge without going through the business of the retarded potentials that we used in the previous set of lectures. It's somewhat simpler. What I want to do now is a slightly more elaborate case, and in this case we're going to think about a line of charge. And we're going to see what that gives us. So in this line of charge, I'm assuming that we've got a line of charge like this. This is going to be the Z direction, and we're going to work in cylindrical polar coordinates. So we're going to have an R, and we're going to have a phi. I'm just trying to work out off the top of my head which way around those should be, and the phi, whoopsie, the phi should of course be that way. So that's our coordinate system. This is a line of charge. It has density lambda, which is a charge per unit length. And in order to calculate, we're assuming that it's at rest in our standard reference frame S. And we want to calculate the electric field. So to do that, we're going to create a cylindrical surface, a cylindrical volume, which is going to have radius R, and we're going to figure out what's going on using Gauss's law. So Gauss's law tells us that the volume integral of the divergence of the electric field is equal to the volume of the charge, which in this case is going to be lambda over epsilon naught dV. Let's tackle the charge first. Since we've got a density per unit length, the result of that integral is going to be lambda L over epsilon naught, where L is simply the length of our cylinder. That length is entirely arbitrary. It's going to cancel out. Now, what we're going to do is we're going to use the divergence theorem. So that tells us that the surface integral of E dot ds must equal lambda L over epsilon naught. And let's just think about that cylindrical surface. We've got two ends, if you like, which are just the circles at the end of the cylinder, and we've got one sidewall, which is the curved outward part. The ends have a normal parallel to the z direction, and the sidewalls have a normal which is parallel to the radial direction. From the geometry of the problem, or if you prefer from symmetry, we can say that E, the field, must lie entirely along the radial direction. You can say that because if you had any kind, you would have to have some kind of imperfection in the line of charge along Z in order to have any component along Z. Similarly, you'd have to have some kind of disturbance to give it any kind of phi component. Because it's purely lined along Z, the only direction that the E field can take on is the radial direction. That means that the ends are going to give us zero contribution. On the ends we'll have Ez is equal to 0, so E dotted with ds on the ends is going to equal naught. So now we only have to think about the sidewall. So along the sidewall, E dotted with ds is just going to equal E multiplied by r hat multiplied by r hat multiplied by ds, which is therefore equal to E times the surface element. So now our surface integral, which is no longer a closed surface integral because I've said that the end caps are 0, is going to be E, and then the surface element is going to be r d theta dz, sorry, not d theta, d phi. I realise I probably shouldn't have used phi because that's going to confuse us, but remember that that's an angle at this point. And so that is the integral, so phi goes from 0 to 2 pi, z goes from 0 to L, and here's our E multiplied by r d phi dz, and that is just 2 pi r L E, which must equal lambda L over epsilon naught. And you'll notice I said that the L's will cancel, and they do. So now we can say that the electric field is given by, let's cancel that as we get a lambda over 2 pi epsilon naught r in the radial direction. That makes all kind of sense. It looks perfectly reasonable, and there is no B field at all. If we now transform to a new reference frame S prime, where the velocity, we're going to take a slight difference, it's now in the Z direction relative to S. That's because it makes the maths slightly easier. Let's think about the fields. Well, so Ez prime is just 0 because Ez is 0. Bz prime is equal to 0 because Bz is equal to 0 and Ez is, so that's those two parallel components dealt with. If we think about E primed in the phi direction, that's going to equal naught because there's no E prime, there's no E in the phi direction, and there's no B field. So the only component of E prime that we worry about is in the radial direction, and that's going to equal gamma ER, because remember we have E primed parallel is E parallel, and E primed perpendicular is gamma E perpendicular plus gamma into V crossed with B perpendicular. So that's the only bit that we need. That's given us the whole of E. What about B? Well, remember, we've already done B prime parallel is equal to B parallel, and that's naught. And B perpendicular primed is gamma B perpendicular, which of course itself is 0, minus 1 over C squared gamma into V crossed with E perpendicular. Now, V is along Z, E is along R, so Z crossed with R is actually equal to the phi direction. So we find that BR primed is equal to 0, because because there's no component from the E field and there's no component from the B field. So the component we are left with is B phi primed, which is minus gamma V over C squared lambda over 2 pi epsilon naught R. But we can identify V lambda as being basically equivalent to a current I, so that implies that B phi primed is minus gamma. We've got mu naught, and that's cancelling the C squared and the epsilon naught, I over 2 pi R. And that, of course, is the result you would get using the Biot-Savart law for the magnetic field from a current carrying wire. Notice the minus sign here is because when we transform to S prime is moving with velocity v relative to s, which means that from S prime's perspective, the current is flowing backwards along the minus z direction, and that's where that minus sign has come from. So we see that we've actually produced something that is perfectly compatible with standard electromagnetism. The factors of gamma maybe aren't standard in electromagnetism, but they're necessary for the transformations, and at velocities anywhere away from the speed of light, they will be negligible. So that's two simple examples of how we can use these transforms and how changing reference frames can change between electric and magnetic fields.